Hi guys, Mark at Cutter Electronics. Wanted to talk today about sol strip boards. Strip builds are probably becoming one of the more common questions in terms of constructing a grow light kit that we get on. So what we'll do today is go through the board in terms of how it's constructed and the topologies that relate to that construction in terms of making a grow light system. It's very simple for DIY users, but if all you're used to is growing plants, coming to LED lighting might be a big jump. So let's have a look at how we go about constructing some kits and the various ways we might do that. Let's consider the sol strip in terms of its configuration. Okay, it is 560 millimeter in length, or 2 foot. It's 14 millimeters wide in this current variation, and it's 1.65 millimeter in thickness, and it's metal core, aluminium. Is that important? I think it's important in terms of dissipating heat. When you compact up that many leads, then you're wanting to dissipate the heat as best you can. Aluminium cost relative to material is the best material selection going around. So the board is made up of 112 leads. That construction is 16 leads in series, so a string of 16, and then those 16 leads are joined in parallel. So 7 by 16 will give you 112 leads. The 16 leads is important in that 16 leads by approximately 3 volt equals 48 volt. That is the operating voltage range of the PCB. The thing to note here is 48 volt is nominal. What does nominal mean? So basically it's 48 volt nominal, however the board can run from say 42 to 48 volt without too much problem. Of course your light output will be dictated to by that voltage and more importantly by the current. So 42 volt to 48 volt is dictated to by the current. I equals current, O equals output. So at 42 volt it might well be running at say 500 milliamp, or you might be running it at 500 milliamp with your driver. At 48 volt it could be 1.2 to 1.3 amp. So the voltage is dictated by the current or the selection of your driver to run the board. So let's consider wattage with respect to these boards, aka power. Why should we consider power or watts? Most people that grow things and have used old style lights, CMH, HPS, or even other variants of LEDs, will often consider a light in terms of its watts, its power performance. So to calculate power performance with these boards is relatively simple to do. We basically need several constants. We need voltage. We need to multiply that by the current, I/O, and that will equal power or watts. So if we look at this board, for example, and let's say that we wanted to run this at 700 milliamp as an arbitrary number. At 700 milliamp, let's assume the board is approximately 44 volts. So 44 by 700 milliamp will equate to 30.8 watts. Now that will be per board, so 30.8, 30.8. It won't really matter whether you're running the board in series or parallel configurations, which we will discuss shortly. But the important thing to note is that if you ran two boards at 30.8, then you would be at 61.6 watts for this particular system. So considering that watts is a legacy, an old style way of defining a board, is watts important with respect to more current LED technology? Probably the most important aspect of watts relates to thermal. Why is thermal important? Heat is the enemy of the LED. Its ability to maintain efficacy, its ability to maintain output, and its ability to maintain colour consistency is ultimately dictated to by thermal performance. And thermal performance is most easily defined by wattage. So if a board is 30.8 watts, and certainly in a board like this that is constructed in aluminium, then the consideration must be, do I heat sink it? Do I need a heat sink or not? And it's a good question which we'll delve into a little later. But the performance of your system is going to be dictated to by heat. So let's look at series wiring in terms of the strips. To start with, we'll look at 3 points about series wiring that are worth noting. So the image to the left demonstrates a simple series circuit with two LEDs. The positive wire leaves the LED driver into the positive input of the first LED. The negative wire leaves the negative position on the output of the first LED and runs into the positive of the second LED. The final negative wire returns back to the driver to complete a series circuit. One issue most people tend to have with the series circuit as a model is that it's counterintuitive to take a positive wire and run it into a negative wire on the LED. And most errors we find with LED setups relate to the fact that people want to wire positive to positive. That's the first point. The second point about series configurations is that it's an additive process. By that I mean that when you have two LEDs in series, as per the example of a 3 volt and a 3 volt LED, when you wire them in series, you add 3 volt and 3 volt to get 6 volt as your total system voltage. The third point, and it relates to the second point to some extent, is that the current remains constant across the two LEDs in this example. So the drawing shows a 700 milliamp driver, and via the black arrow you can see that the current is constant across both LEDs, even though the voltage has been added together. So the term constant is important in that in most instances with series circuits, constant current drivers are used. A constant current driver will notably have a wide output voltage range. In the case of the drawing as displayed, we have a 5 to 36 volt output. So this 6-volt configuration demonstrated falls within the 5 to 36 volt range, and therefore output of 700 milliamp is a constant current and is not altered or changed by the fact that there are 2 leads in circuit. Okay, so if we wire the boards in series, let's configure the boards. So this is your lead driver. Likely that it will be an AC input, not always. And out of the lead driver on the secondary side will be a positive and a negative output. It's likely that you will possibly have dim, but at the moment we'll just deal with the wiring. So in a series configuration, the output in terms of positive, the first wire will go into the positive input on the lead board. Exiting from the negative wire, you'll then take that to the next positive input, and continuing on negative to the positive, and completing the circuit will be your negative wire back to the driver. That's a completed series circuit. And of course you can go on and on. The limiting factor, of course, is the capacity of your driver in terms of volts, current, and wattage. So let's consider the use of a parallel wiring circuit with these strip boards. So as we've used in series configurations, we need a driver, and we need to wire that driver to the boards. This particular version is a constant voltage driver. It can have dimming capability, but we will deal primarily at this point in time with wiring to the boards. So what we want out of the driver is a positive and a negative. So with parallel, it's somewhat simpler in that we run fundamentally a rail and connect both anode and cathode, or positive and negatives, to those rails. So here we have a plus and a negative, a plus and a negative that returns back to the driver. So it is somewhat more intuitive and simpler than using a series configuration, but some of the same rules will apply, and that is the capacity of the driver will dictate the amount of product, the amount of strips that you can have on the driver. So let's consider this in some more detail. So the lead driver, we will say its output at secondary side is 48 volt. Now, this can be fixed. It can be semi-fixed in that you can have meanwhile drivers that have a current and voltage adjustment, or you can have a B version dimmer which is fixed in the sense that 48 is the maximum, but you can dim down to a lower voltage current level. So 48 volt is coming out of the output side. In a parallel circuit, 48 volt is being delivered to each circuit board. So 48 volt, 48 volt. So it is not additive. A parallel circuit, however, is divisive. Possibly not a great word. It divides. What it divides is the current. So that if this lead driver, as an example, was 1 amp as its maximum output, then the driver is still maintaining 48 volts in a parallel circuit to each LED board, but in a parallel circuit the current is divided, and the current is divided by the N, or number of strings. So in this instance we have 2 parallel strings, and therefore 1 amp divided by 2 is giving us a 500 milliamp per string. So why don't we consider this in terms of a real world scenario, and it'll to some extent explain why parallel circuits for strip boards are typically the topology of choice by people building strips. So if we take, for example, an HLG 600 H-48A driver, it has 12.5 amps of total capacity. And therefore we can divide that 12.5 amps at some nominal current that we would like to set per board. Look at this in terms of the different quantities of strips. So if we divide 12.5 amps across 12 strips, we would be running them at approximately 1 amp. 16 strips, divide 12.5 divided by 16, we have 0.78 amp. And 20 strips would be roughly 625 milliamp, or 0.625 amp. In terms of capacity, we must remember also that the wattage of this particular driver is 600 watts. So it doesn't matter really how you skin the solution, you're limited in terms of total wattage to 600. So 20 strips, each strip will be running at 625 milliamp, or 0.625 amp, at 30 watts per strip. So 30 times 20 equates to 600 watts, which is the capacity of the driver. So the driver is fairly well tapped out. With an A driver, you do have a little headroom in that you can dim both the volts and current settings on those. So you do get a little headroom for driver overhead. Okay, so we've covered series wiring of strip boards, and we've covered parallel. So there is a hybrid version that uses a combination of both, called series parallel. And we'll look at that, but let's think about it in the context of what we've so far discussed, in that series based designs probably are better suited to constant current. And parallel based designs are probably better with constant voltage. And the reason that this is so is primarily because in series-based designs, the voltage is additive, and in parallel circuits, the current is divided. And that works better with a constant current and a constant voltage driver in those circumstances. So if we look at a hybrid series parallel, there is an opportunity to utilise a combination, or potentially a specific driver that will meet those requirements. So what we have here is a series parallel circuit. So to clarify, the rail is parallel, and across the parallel rail we have 4 boards, 2 lots of 2 in series. On the rail, we're going to put 96 volts, or we could use a driver that's constant current in this example, let's say a maximum of 114 volt. So a regulated constant current will provide us with 96 volts, and we will get 96 here and here, and the additive process will provide us with the 48 and 48, which is the 96. So these boards are in series. If we look at this from a calculation perspective, this particular driver we will say is 2 amp. So with a parallel circuit, what will happen, of course, is that that will become 1 amp on each leg, and we will now have in series 1 amp across the two boards that are both at 48, 48 at 96. So in terms of our calc, current is 2 amp. The current in parallel circuits is of course divided, and in this case not by the board per se, but by the number of strings, 2 strings. So we'll divide 2 amp across 2 strings, providing 1 amp at each string, and that 1 amp is of course actually at 96 volt. That is a series parallel circuit, and is useful in that you can use a constant current driver rather than a fixed voltage driver that typically would be a constant voltage driver. Not many CV drivers will run to something as high as 96 volt. So it's a useful way to use a driver that you might have that's constant current that nominally wouldn't work in a series, in a parallel string circuit.